Back in 2018, I started playing with some transistor amplifiers, and it was like small modules with cheap transistors, and they worked, but they didn't work as well. But this time it got very serious, and I decided to give it a shot with some proper transistors, and basically I had only limited tools, but you will see it came out really well. Okay, for me, this was the initial test. This was how it all started. And in the beginning, this was the basic setup. It's bare bones, but it worked. But I don't recommend running it like this because I killed my first transistor already, so it was a no-go. So after some iterations, this was one of the final versions, and I have put a lot of effort into this, and it has many features.
Too fast, go back.
Too fast? Okay.
Sit down and 5 days.
Too slow.
Too loud.
Too normal, too normal.
Okay. So these were some design goals I wanted to incorporate in my amplifier. So it has water cooling, it has all protections like all the other amps. I wanted to cover all the bands. Of course, all the goodies these new amplifiers have, so it was a quite big challenge for me. And I started with the RF deck first. So this is the picture on the right. This was my first RF deck. I made it back in 2019, and I was following some application note from NXP, and of course it did not work. And, of course, that's such a surprise. And picture on the left is actually how it looks right now, and this is like version 6 or 7, something like that. And this one is good. So, and of course, while I was building the RF deck, I was very impatient, and I wanted to test it somewhere else, because I was testing it only into the dummy load, and that was kind of boring, so I quickly made some setup to run it with a real antenna. So this was the first on-air test, and it worked. So that was good. That is a really good feeling when something works, when you make it with your own hands. So in 2018, I started the University of Electronical Engineering and Computing in Zagreb. And this picture was taken, I think, at my third year at the university. I had an idea to combine my thesis and my hobby, basically the amplifier, and I brought everything from Dubrovnik to Zagreb and started working on it there full time. So up to this point, I was working only during the summer and during the winter when I was home. So it was very little work, but now it got serious, and I worked on it every day for a couple of hours. So I would like to start with some mechanical construction. This was very challenging for me because I had very limited tools and almost no budget, of course, like every student. But there was a lot of workarounds and tinkering. So, for example, I bought some tubes from the local store, these square tubes over here in the second picture. And then there was a problem how to put a screw in the tube. It will strip out because it's very thin. So basically, workaround was to put iron pieces in the tube so you can screw it around many times and it won't strip out. That's one example of workarounds. And okay. Yes, and I had very limited tools, as I said. I had some basic tools, some power tools, and a homemade CNC machine. That's all I had. So you can see the bare bones of the mechanical construction. My idea was to make the backbone of the amplifier like this, so you can have access from every side of the amplifier. So it's very good for servicing, for measuring. So you can basically open every panel and access everything from every side. And of course, that wasn't easy to accomplish. So you can see here are some prints in some CAD program, because I need to visualize everything, and it's not simple because there is many parts. And you can see here all the different layers, drawings, plans. So it took a lot of planning, but it came out good. So this was some midpoint after 1 year. It was already coming together slowly, but it was not fast enough. I was very impatient, I don't know, but I guess I was excited, and that's why I was so impatient. But yes, it was also very nice seeing it all fit together after so much tinkering, planning, and everything like that. So, this was almost completed mechanical work on the amplifier. Everything was there, but the front panel was still missing. It was a mystery for me how to do it, because everything else turned out so nice, and I didn't want to make it look bad, I wanted it to be nice and sleek as everything else.
Like our
Or better.
Just say beautiful, it's okay to say.
Okay. So this was the very interesting part in how I made the front panel. Before I had some experiments with melting metal, so that's very interesting and very dangerous, of course. And my idea was to make a mold. You can see it on the right side. Melt some aluminum, pour it in, and basically make a piece yourself, because it's a very thick piece of aluminum. It's about 1 centimeter, and you can't buy it anywhere. It's very expensive to buy it, and I had no budget, of course. So you need to make tools. Oops, what happened?
Sorry.
Thank you very much.
That's it. No, that's not it.
Quick question in meantime.
Yeah, I'm listening. Oh, my thesis was the whole amplifier, the whole...
Yeah, but is it finished? What was the mark? So what the
Oh, it was an A, of course. It was finished. Yeah, it's a very big project, so it's a bit maybe too much for one person to do it.
Yeah. Cable.
Oh, the cable is the problem. Okay.
Mirko is the problem.
So okay, yeah, I needed to build everything, so I needed to plan out the mold, I needed to build the furnace, you needed to make this metal container, you need to weld it up, and of course, this wasn't the first try. I made 4 tries until I got this piece in the middle. You can see maybe here, this was the try number 2 or 3, I don't know. There are many problems. You have bubbles of air inside trapped, so it doesn't look so good. But yeah, when I got that good, I put it on the machine, and me and my father machined it for 10 hours straight. So it was a very labor-intensive thing to do, but it's very, very rewarding.
The mold was made of what?
The mold was made of some blocks. I'm not sure how they are called, but they are white and filled with air, some construction blocks,
okay.
very soft.
Separate.
Something like that. So also one very important thing for the good amplifier is cooling. So if you don't cool your amplifier properly, it will burn out very quickly, and I learned that the hard way. So I have always wanted to try water cooling, and I had by accident a piece of copper about 1 centimeter thick. I cut it in half, machined the parts, so I machined the grooves inside for the coolant to go through, and I soldered 2 halves of the copper with regular tin. And I also opted to solder the transistor, but I used different transistor. I used lower melting point solder, so I wouldn't burn out the transistor because he can't take that much temperature. And of course, it took me 3 or 4 days to complete this. There was many holes to make the taps inside, many holes, but they're very shallow and the copper is very sticky, so it's very tricky to do it. But if you do it slowly, it will be okay. And as the result, the cooling is working very well, maybe too well. The temperature never exceeds 40 degrees Celsius on the transistor here, measured over here. So I would call that a success.
Try to measure it at the gates.
Okay, that's a smart thing. And of course, there was a lot of mechanical construction, and I had many pictures. I have about 2,000 pictures of construction, but it's very difficult to take a few important pictures to explain everything in such little time. But I will touch here the software side and some PCB side. So I used all the tools that are open source, that are free, that you can take on the internet, and they are free to use. So this is the list of all the softwares I used to build the PCBs, to program everything. And I would like to show a few important PCBs in the amplifier. They are not the only PCBs, but they are some of the most important inside. So for example, we have the RX-DX unit and the power meter. I opted to do it on the same PCB, so it's convenient for me. And of course, I put 2 relays because I like to do sequencing between the input and the output, so it all works properly. And you can see it here on the left picture how it's mounted inside the amplifier. So this is the filters, this is the module, and this is how it's all connected, integrated. So it's working very well. The power measurement is pretty accurate, up to 6 meters, about maybe 0.2 decibels of mistake there, but that's very good. So this is the next very important thing for the amplifier. Every amplifier needs a protection board, so you can protect it from overdrive, from SWR, from wrong filters, from over temperature, from overcurrent. So this was my version of the protection board. It's all analog, and I made it on purpose all analog, so it's very fast. About 1 microsecond is the response time of the slowest protection. So that was quite a challenge to do it properly, but I managed to do it. This was the version 1. Also, very important thing was the attenuator board. This keeps your gates alive from overdrive. So from here, the power of the transceiver comes here. You have a coupler which measures your forward power into the amp. You have attenuator. You can put 10 dB, 15 dB, it doesn't matter, whatever you want. And I have here some limiting diodes. So it cuts off the drive. So after 2 watts, it cuts everything, so nothing can go through. And for fine tuning, you can put extra attenuator behind the limiter. So this part is the primary overdrive protection, and this part is actually the part of the secondary overdrive protection. So I take a signal and I feed it to the protection board. So these protect from the spikes, and these protect from the constant overdrive. So it shuts off. And of course, the brain of the amplifier, the control board. Here So here we have the control board. So it does all the measuring or the hardware to software levels and many things, many different protocols, sequencing, and so on, so on. And this was maybe the most difficult PCB for me to design. It took me about 3 months to design it, because there is a lot of different protocols like USB, CAN interface, I2C, many different protocols and analog measurements and very fast signals. So it's a big mess to control everything so it doesn't interfere one with another. So it does all the low-level integration, and of course everything comes out the small USB here, and it's connected by a blue cable, if you see it over there, to the Raspberry Pi 4. That is the second brain of the amplifier, which does the user interface. More about that a bit later. So after 3 years, this is the complete amplifier. This is how it came out. It looks very good, but you can see some problems already. The paint started to chip, but that's okay. I see that, you probably don't see it, but that's in the eye of the maker. Okay, now we have the user interface. So as I mentioned before, I use the Raspberry Pi 4 with touch display. You can see it over there. And this is the user interface, how it looks in normal operation. So it has all the power meters, SWR meters and everything. But of course, it's all written at home. The code is written in JavaFX. So all of these meters and everything were written by me and my father, which took us a lot of time to make it work, because you make 1 meter, then you put some signal, then it all blows up, all the errors and everything. So it was labor intensive. And of course, one very important feature that I put in my amplifier was that it was designed to be the center of my shack. So you have the amplifier, and it's all connected via a messaging system. I used the MQTT messaging bus at the home, and everything is connected with wireless. So for example, you have the compass module for a heading, antenna rotator. You can connect via VPN to the amplifier, and the amplifier can sniff the broadcast messages from the wind test or every other log, so you can find the mode, the band, the frequency. You can control external antenna switches, filters, and I will go back. Maybe you can see here, this is the antenna select. So when it connects, your antenna shows up here, and you can select your antenna from the amplifier. Of course, you can use auto, manual, RF sense mode, whatever. And of course, when it connects to the log, it automatically takes your mode which you're running, and it optimizes the working point of the amplifier. And of course, you have antenna rotator. Here, when you select, for example, 20 meters, here the heading shows up, and you can rotate the antenna from the amplifier. So that's very neat. So no boxes on the table, everything is stowed away, and much less cables. And this is basically it. So these are my conclusions. It was a very difficult project, but very rewarding. And it's all possible with some tools and stubbornness, of course. And you don't need to be cheap. For example, if you have a box and you came up with the idea, okay, let's build the amplifier around the box. No, that's wrong. That's a way to compromise from the start. So I crossed that out from the start. And of course, prepare for disappointment, because stuff usually doesn't work, and that's confirmed many times. But it's the best case, because you learn the most from the failures and when you make it work. And of course, I want to thank everybody who helped me, my family, everybody else. I want to thank Ranko for the help and the filters. The filters are from the Power Genius, so thank you very much, Ranko. And I'm just very glad that I didn't, how do I call it, just a moment, that I didn't give up. So I wanted to give up many times, but I didn't in the end. So that's it from this short presentation. Any questions?
What's the output power?
The output power is 1.2 K, nothing much.
What is input power in different bands?
Input power is between 25 and 28 watts for full power.
You go up to 6 meters?
6 meters, yes, with some bit less gain, but I limited it to 900 watts on 6 meters.
Because of that, I was asking how much input power.
Yeah, because I limited it with fixed attenuators and diodes, so 25 watts into the amplifier is the max. So after the attenuation, it's 1 watt into the gains.
I know this. Just I wanted to know the difference in gain.
The gain is compensated by different voltages
Okay.
from the power supply. That's the simplest way to do it.
Any plans to give the PCBs and project free for others?
Yes, but they need to be a bit more optimized because this was managing with materials I had left, so it could be better in some parts and it's maybe a bit too complicated in the other parts. But I can give out PCBs.
How long can you stay with the K down on CW?
With the K down on CW, you can stay at least 5 minutes, until the temperature rises to 50 degrees Celsius, so that's the cutout for me.
50 degrees cut out.
50, 60 degrees, something like that.
Yeah, because he is measuring on the side of the transistor.
Yeah, the temperature is almost 2 times inside on the crystal.
How is with the band changing?
The band changing is automatic, so if you press maybe 20 meters on the transceiver and you have the log, the message goes via CAT to the log, and the log broadcasts it on the internet, and the amplifier sniffs out the message and automatically takes the mode and the frequency.
Do you measure the frequency?
I measure the frequency because the filters are diplex filters inside, and you can't know if you selected the wrong filter based on the SWR measurement, so I need to measure the frequency.
So even without the cat, you just put a little signal and it switches?
I don't like to do that. I blocked out that option because it stresses out the relays and everything, and I didn't design it to do that from the start, so it's stupid to add it after that because it would need some modifications. But I don't need it generally. I always run the log and the transceiver.
Which transistor?
I'm using MRFX 1K80H, so it's 1.8 kW version.
Did you try other ones?
I tried 1.5K, but that one died. This one has the higher breakdown voltage, so I picked it out.
What's the weight in kilograms?
I haven't measured the weight, but it's pretty light compared to the other tube amplifiers. But I think it's 10 to 15 kilos, something like that.
Regarding the water inside,
There is very little water inside, actually. There is about this much if you fill the cup. This much water is in the system.
Do you refill it from time to time with the water?
It can be refilled. There is a port for refilling, but it usually stays in the closed loop, so no refilling needed.
Does it have antifreeze inside?
Yes, antifreeze from the gas station.
yeah, because when you go to the custom to some expedition, you can't pass without the MDS report for the what the liquid is inside.
I mean, you can drain it out and pour a new one.
Salty water inside from the Some Island expedition.
That's not very smart,
yeah.
because different metals
And
inside.
How do you cool the liquid?
Can you repeat?
How do you cool the liquid?
Okay, just a moment. I will go back so you can see better. So you can see here. Here is the cooler for the PC. For the gaming PCs, you have a small cooler. I have 3 fans on it, and it's more than enough. And they don't need very high speed for cooling. So it's very cheap, maybe 20 euros it costs.
quiet?
It's quiet. The loudest thing is the fan from the power supply. The power supply is located here. It's from a telecom power supply, so it's a bit loud because it has a small fan, but the speed can be regulated.
How
But-
do you treat the voltage?
The voltage,
It does have different voltage?
yes, it has different voltage, so the voltage can be changed via CAN bus, so it's software communication, and it's changed automatically depending on the mode. So the RTTY has the lowest voltage, CW has a bit more, and SSB has the highest voltage for the linearity.
Do you fix the bias for each voltage? Or?
Yeah, there are 3 bias settings. So if you can see here, these are the bias settings, these 3 potentiometers.
And you can change it depending on the mode?
Yeah, it's automatically changed on the mode.
You change the mode from head control or you automatically detect the...
I'm ready.
No, sniffing.
Can you repeat?
Do you change manually the mode or it detects the...
You can change it manually, but it detects automatically with the band. So it's all automatic basically. Just need to press the button on the transceiver, which band and which mode. Everything else is automatic. The antenna switch, filters, mode, everything is automatic.
But over the cat. No sensing.
Over the cat, yeah. No sensing because it's not easy to sense the.
That was visible.
It's not easy to sense SSB properly. It's a very difficult thing to do.
One antenna output.
One antenna output.
Are you planning to sell the concept and commercialize it?
I have thought about it, but I will see after the university. I don't have much time to play around with this because you would need to take a lot of time and effort to develop it even more.
How did you do the temperature compensation?
Okay, the temperature compensation is very simple. I did it with one diode, but you need to find the correct diode which has the opposite temperature coefficient like your transistor. And it works up to 60-70 degrees very good. So the bias changes maybe 10% over that range. So that's okay for me.
How many transistors died after you finished it?
One died in the building and one died 2 months ago. So that's 2.
Reason?
A reason for the first one, not soldered properly.
Okay.
Second one, I don't know. That's the problem, I don't know why.
But it's LDMOS, so you...
Don't bother, leave it 10 experience.
And I have tons of protections and nothing activated, so I'm not sure yet.
What was the total time from the idea to the finished product?
Time from the idea to the finished product.
3 years.
If I cross out the time at the uni, maybe 2 years with some breaks, but around 2 years with normal working time. From zero, mechanical, electrical, everything.
What's normal working time?
Sorry?
What is the normal working time? 8 hours a day.
I mean, no, let's say 5 hours a day.
Okay, a lot.
Yeah, there is a lot of time, especially if
you learn a lot.
if you do it alone, then it's very labor intensive. There is hundreds of hours poured into this.
What's important to say is now finishing here at the university. In the same time, he finished amplifier, but his nothing is going on without any breaks.
The kind of the filter is the what? The duplexer or the...
Diplexer filter. It's Power Genius model, so if you can recognize it by the box.
If you do it again, what will you do differently?
Maybe put 2 RF decks and a combiner, so this one does not run at its limit. 2 transistors.
To double the problem.
And remove the power, remove the current to the little bit less, to be the 1.5 clearly.
Yeah.
Do not damage the transistor when you're not antenna. Yeah?
And the preheating one because it's most linear.
And the bias? This is the voltage of...
This is the voltage on the drains, and the bias is also different.
Ah.
So to get the corresponding current, you need different bias, of course, at the different drain level voltages.
How much do you use the bias? What has to be for a CW? What has to be bias?
I'm not sure completely, but it's around 3 volts.
No, I'm not asking the voltage, I'm asking about the current.
Oh, IDQ. So RTTY is about 0.8 to 0.9 amps. The CW is around 1 amp, and SSB is 2 amps.
Good.
When you move the resistors, did they completely dead or only half? Did it look not noisy?
I mean, mine blew completely, so both sides were dead. Yeah, the most difficult part when you have to disassemble it all. And one maybe not such a good thing is the transistor is soldered and you need to disassemble half of the amplifier just to take the plate, heat it up, unsolder it, machine it. That's a bit of a pain to do it. Thank you very much.
Стави сам първи слайд.
Ова или следващия?
Да. И ти да презентираш.